radical addition of hydrogen bromide. So in Chapter 8, we looked at alkenes, and we added pure hydrogen bromide, and the bromide added to the more substituted position. So we've got this down here. We've got a green carbon, and a pink carbon. Go back to making it green again. Here's our green carbon. The green carbon is more substituted because it has two R groups off of it and a double bond. And so what we found is that we added the bromine in this position and the hydrogen to the less substituted position. And we called this a Markovnikov addition. We also had a reaction, and we explained the mechanism for this one. We gave the mechanism. We also had a reaction where we had hydrogen bromide, but we added peroxide to it. And we found that when we did this, we added the bromine to the less substituted position, and the hydrogen went on the more substituted carbon. Just the reverse. And so now it's time to look at what the mechanism is for this anti-Markovnikov addition. So there are two initiation steps to produce a bromine radical. First, the peroxide needs to cleave, a homolytic cleavage that gives us two peroxide radicals. This is an endothermic reaction, takes energy. This is what we need heat for, to make the reaction go. Then our peroxide radical extracts a proton from the bromine and produces a bromine radical. And this is what's going to go on to the propagation steps. The bromine radical will add to the double bond here, and it will add in such a way that it adds to the less substituted carbon, because that makes a more stable radical. If it added over here, where it's green, then we would have a radical on we'll do a pink. There'd be a radical on the pink carbon, and it would be secondary, and that would not be as favorable. And then we get rid of this radical by reacting it with hydrogen bromide. And this are the propagation steps. They go over and over and over again because we regenerate our radical here so that it can come back up here, and repeat the process. So you're trying to make stable intermediaries, and that's why in this case the bromine goes to the less substituted. Let's look at the other process and just remind ourselves what happened in the ionic process. Here, the pi electrons attacked the hydrogen, and we were left with a carbocation intermediate. And we wanted this hydrogen because it's added first to go to the less substituted position. And the bromine then goes to the more substituted position. If you look up here, the bromine is added first in this process. And so the bromine goes to the less substituted position, leaving the more substituted for the. So that's the difference. It's the kind of the order. With the radical process, the bromine goes first, so it goes to the less substituted position. With the ionic process, the hydrogen goes first, so it goes to the less substituted position. So let's look at the thermodynamic considerations of this reaction. When we were doing Markovnikov addition, we were able to use hydrogen chloride, hydrogen bromide, or hydrogen iodide. But the anti-Markovnikov, we only used the hydrogen bromide, and now we'll find out why. The first step of the propagation is the radical addition to a pi bond. And for hydrogen chloride, the enthalpy term is negative, the entropy term is positive. For hydrogen bromide, negative and positive. For hydrogen iodide, they're both positive. So this reaction is not going to go. It's not ever going to be spontaneous. Okay, if we look at the second propagation step, we find that the hydrogen chloride is positive, and so that is going to be a no-go. And of course, this is so Br is only negative, has the only negative delta H. Stereochemistry for the radical addition of hydrogen bromide. If a new chiral center is formed, you're going to have a racemic result because you've got a flat intermediary. That radical is flat, and so it can be attacked from either side. If you're trying to predict the products of an addition reaction, you need to identify the two groups being added, ID the regional selectivity, and then figure out the stereospecificity. So let's predict these products. And again, you may want to stop the tape and give yourself a chance to try these on your own. So let's predict the products. We want to consider whether a chiral center is being generated and then draw all the stereoisomers. So what we're going to be doing is we've got a carbon here and a carbon here, and we're going to add a hydrogen to one of them and a bromine to the other. Because this is a radical process, we've got the peroxide here, we know we're going to add the bromine to the less substituted carbon. So we'll get something that looks like this, and we'll have the bromine added here. This is our original double bond between these two. And we'll have a hydrogen that's added up here. Now we need to consider whether we've made a stereoisomers, and we in fact have, because these two arms are different from each other. This arm is different from this arm, and so we've made this compound with the methyl group up, and we've also made this compound with the methyl group down. So we've made two compounds here. So let's look at the next one. We're going to add hydrogen to the green position, and we're going to add a bromine to our less substituted pink position. So let's draw the hated five-sided figure. And the hydrogen goes on the more substituted, and the bromine goes on the less substituted. And now we need to look at this and see whether we have made a chiral center. And in fact we have. We have a chiral center right here. We'll make it black. We've got four different compounds attached there. So we're going to need to draw. One of the bromines is coming toward us, and we'll have to draw a secondary figure where the bromine is going away. Okay. So let's do this next one. We've got a less substituted position and a more substituted position. We're going to add the bromine to the less substituted position. So we are going to go back to the green. We've got this, and then two arms that stick up and down, and the bromine is going to be added to the less substituted position, and up here we've added a hydrogen. Now we've not made a stereoisomer here. So we have no chiral centers, and so we don't have to draw any other figures. Let's look at this last one. Once again, the hated five-sided figure. We're going to add bromine to one side and hydrogen to the other. We don't have any chiral centers, and so we're done.